Let's talk about a different breed of service meshes today. Hello, my name is Matthias, and I work as an engineering lead at Spotify for the compute networking platform teams. At Spotify, we do load balancing a little bit differently. If you design your backend topology, you really have two ways to do load balancing. You have server-side load balancing, and you have client-side load balancing. Server-side is very common, right? You have your backend services and instances, you put a proxy in front of it, and that proxy takes care of monitoring all those instances' health, how they feel, the load they serve, or the outstanding requests. And when you make a request to the service, you do that through the proxy, and the proxy decides where to send the traffic, kind of balances the load. That's great, because you have this one place in the middle that centralizes all of your configuration in terms of traffic. It's also bad because you have an extra network hop from your client to the service. So at Spotify, we've been using client-side load balancing for some years, and where the load balancing is actually happening in the client, the caller. You don't have a proxy in between. The caller needs to be aware of what's happening in the backend, kind of needs to be aware of all the topology, needs to health check everything himself, and then makes a local decision. What you get out of this is you get very low latency. There's no extra network hop, which is great, at the cost of a very complex client. And if you want to roll out any changes globally, that's going to need a lot of coordination across thousands of clients. A few years ago, we started using gRPC at Spotify, and gRPC has a third way to do load balancing. It's called look-aside load balancing. You start out with a client-side load balancer. You kind of extract all the logic needed to make routing decisions and move that into an external component, the look-aside load balancer. Then when the client makes a request to the service, it looks aside, out of band, to that load balancer to get a list of instances that it can call, and then it makes a direct connection. So you still get the client to service low latency connection, but you also get to control that centralized in one component. I almost forgot, I included a small little dog in the corner. This is a golden retriever. Its name is Pancakes. If you spell it out, it's golden retriever pancakes, gRPC. This is the official mascot of the gRPC project, which I think is amazing. In itself, a good reason to do gRPC, by the way. I'm getting sidetracked. Where was I? Yes, load balancing. So if you take the look-aside load balancer, tilt your head a bit, you might recognize that under a different name. This looks like a service mesh. Let me show you. Traditional service mesh, you have a data plane, that's the red stuff on the graph, and you have the control plane. In Istio, that's what Istio is, the blue area. And in the data plane, you have a service A calling a service B. It does so through local proxies that are running locally to the service instance, and the proxies decide how to communicate. Those proxies, in Istio, they're Envoy proxies, communicate with the control plane through an open protocol called XDS. And now the real kicker here is gRPC has native support for XDS, the same protocol. So if you use gRPC in your backend, in your services, you can get rid of all those proxies, and now the control plane can directly speak to gRPC clients and tell them how to reach service B without any proxies. So conversely, the gRPC clients, talking to a look-aside load balancer that I mentioned before, the look-aside load balancer is the control plane, is Istio, or at Spotify we use Google's control plane, but the concept is the same. You can now program your data plane, your gRPC clients, from the comfort of your control plane in one place. So, you get all the benefits of a service mesh without having to pay the proxies tax. Thank you.